In this video, we're going to conclude our discussion on rational functions and their graphs. And specifically, we're going to be talking about this situation when we have something called a slant asymptote. So we'll get to that momentarily. For our warm up today, I want you to think about this question. When we talk about a function having a horizontal asymptote, what are we saying about the function and the asymptote? And it's hard to ask a kind of a deep level question without sort of giving away what I'm looking for, but try to avoid just a surface level definition answer. So we should really think about what it is that's happening and what an asymptote is compared to the function itself. So I'm going to ask you to pause the video and then check back in for what will probably be my rambling answer. Okay, so there's lots of ways to think about what a horizontal asymptote is, and I've been trying to drive home the point that it's certainly a discussion about the end of behavior. So anything we discuss here, we need to really be making sure we understand that when we're talking about the horizontal asymptote, what we're talking about is things, what's happening on the function on the far reaches. So this is an exaggeration, of course, but let's like at a million and further out. Now, usually, of course, this is going to start to take shape much before that. But just to wrap your head around it, I want you to realize that we're talking about the extreme ends of this graph, like what ultimately happens here. And if it has a horizontal asymptote, then what we're saying is that our graph, the outputs of the function, as x gets further away from 0, the outputs of the function start to stabilize at the same number. And so if we made a table of values, we would see that show up as tiny little decimal point changes out to the millionth and trillionth places, but essentially the number stays the same. And so on one level, it could just be that you could say that the outputs all become the same number. You could say that we approach a value and don't necessarily reach that value. But the one thing I really want you to think about with what a horizontal asymptote is you can also think of an asymptote as a replacement of the function itself. So you can graph, like a very complicated rational function that does all kinds of, weird stuff, in this range around 0, but eventually, it starts to do something like this possibly. So when we say there's an asymptote at y equals 0, basically what it's also saying is that we could go out to this million and further, and if I graphed y equals f of x and I graphed y equals 0, they would look identical. And so essentially we could also think of an asymptote as a replacement, that the graph simply becomes essentially y equals 0. So if we were looking for a shortcut to graph this, if I said make a table of values or otherwise figure out what this graph looks like on a domain of 10,000 and greater, then all I would expect you to do is, if you knew the asymptote was at 0, then just graph the line, y equals 0. That's what our graph will look like in that range. All right, so an asymptote, lots of ways to look at it, and different times it's convenient to look at it in different ways. It's a line we approach. It's a line that you could use to substitute, etc. Let's move on. Example number 1, let's analyze and graph this function. So the first thing I want you to notice, we should always sort of consider is our asymptote situation. And this appears to be a pretty straightforward question with an asymptote at y equals 3, a horizontal asymptote, I should say. Because we look at the degrees of the function are the same, and we have a ratio of 3 over 1. So I would say we have y equals 3, so nothing special here. And before I do anything else, I really should factor this because I see all kinds of factoring. I can factor out a 3, leaving me x squared minus 1. And on the bottom, I get x squared minus 9. So this will all factor into 3 times x plus 1, x minus 1, x plus 3, x minus 3. All right, so on this one, I don't think there's going to be anything special or new that's going to happen. This is just kind of a warm up for us. Our horizontal asymptote is easily answered if we look back at the original, so we did that. My vertical asymptote, none of our trouble factors in the denominator canceled, so we know we have a vertical asymptote at each um, -3 and +3. The fact that the horizontal asymptote is 3 also is nothing to do with that, right? The horizontal asymptote had come from the fact that we have 3 over 1. The vertical asymptotes have to come from the fact that when we factor the denominator, 3 and -3 makes 0. All right, therefore we have no holes and zeros. Zeros and intercepts, what we have left. And we know that we have a 0 at x equals 1 and x equals -1, which of course is referring to then the intercepts, the x-intercepts of 1, 0 and -1, 0. And a y-intercept, plug in 0, and I would do that all the way back at the original function, not at the factored. And I get -3 over -9, which would be 1/3. All right, let's see what we know. Horizontal asymptote 1, 2, 3. Label it. Vertical asymptote at, that's weird. I wrote x equals and y equals. -3, +3. Label. I have zeros at 1 and -1. I need to label those, but I'm going to wait to label them. And a y-intercept of 1/3. All right. The good news is I know exactly what this graph looks like. As you've undoubtedly heard me say, the lack of data is data itself. And so when I'm considering what the graph looks like over in the domain of 3 and greater, I have no intercepts over here. My little clicker's not working, so if you can see my little dot. And so that means my function has to be following my asymptotes up here. The only way I could have this graph work out is if it looked like this. I suppose there's a remote chance it came down and bounced again, but that just isn't going to happen without some pretty miraculous stuff going on in the function. And again, no zeros over here, so my function has to look like this. All right, and so there we go. And again, just to drive home that point about that horizontal asymptote, notice the horizontal asymptote has nothing to do with what the function looks like anywhere near 0. But once we get out, past a certain amount back here, then my line, my curve, and y equals 0, other than my crappy drawing right there, essentially become the same. All right, so that was pretty simple. Illustrating again why I like horizontal asymptotes not at 0, because when they're not at 0, then I already know the absence of any x-intercepts help me figure out where to make the graph very quickly. All right, so let's look at B. All right, on B, I want you to notice that, in fact, we have a new situation, possibly new situation, I guess, where the degree on top is bigger than the degree on the bottom. So if we think about number sense, as x gets larger, then the numerator outgrows the denominator. And so the bigger the x, the bigger the y. So this is going to be a situation where it continues to grow. So we do not have a horizontal asymptote. So in my analysis, my first thought needs to be about my horizontal asymptotes, and we have none. And then we'll get to the implications of that shortly. All right, can we factor the top? We need to add to get a 5. That does not seem possible. So I do not think the top is going to factor very nicely. I'm just looking at another time here. Yeah, that does not appear to be factorable. All right, so we are definitely short of information on this problem. One thing I do know is I have a vertical asymptote at x minus, I'm sorry, at x equals 2. Um, and I know it's not a whole because there's no factor on top to cancel out that x minus 2. Whew, that's really about all I've got. I mean, the zeros I'm going to have to find, but I'm going to have to use maybe the quadratic formula or something for that. Um, so let's talk a little bit about the end behavior on this function. When we are thinking about end behavior, we're letting x get very, 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 very large. Um, and in a situation where we have the numerator on top greater than the bottom, then that sort of implies like an improper fraction situation, right? So what we have here is sort of the number equivalent of, let's say, 7/2, where the degree on the top is bigger than the degree on the bottom, and so it makes it kind of improper. And so, in a case like 7/2, 2 doesn't go into 7 directly, so we cannot just simplify that to be 3. But that doesn't mean we can't still divide it, right? We still can divide it and go to a mixed number. So we divide 7 by 2, and we get 3 and a remainder of 1 over 2. So we get 3.5. So let's do something similar on this one. Let's do long division, or division. I guess we could do synthetic. And let's see what we get. So I'm going to go ahead and do long division just because I think it illustrates a little bit better what's going on. But you can use synthetic if you would like. So I get x minus 2. So that's going to be a 3x. So I get 3x squared minus 6x. I'm going to subtract, which makes that a positive x and a 5, which makes this a positive 1. And I subtract, and that makes 7. So we get 3x plus 1 and 7 over x minus 2. So when I divide these two, I get this answer. So one could basically think about the fact that this is the function that I'm graphing, right? This is like saying in its given form over here on B, this is kind of like saying, oh, you have the number 7/2. Well, 7/2 is 7/2. That's the number. In this form, it's kind of like we divided 7 by 2 and we got 3.5. 7/2 and 3.5 are the same number. They just are in a different form. That's exactly the same case we have right here. If I were to make a table of values right now, using the given f of x over here, or the given, or this simplified, let's call it f of x, we should get the same values. And we could test that to find out. Let's just plug in one number to see that it's true, at least seemingly true. If I were to plug in 0, I need to find my y-intercept anyway. So let's find our y-intercept using both functions. I plug in 0, I get negative 5/2. If I plug in 0 over here, the 3 goes away, I get 1. Plus, I plug in 0, I get, turns into a minus 7/2. Well, 2/2 minus 7/2 is negative 5/2. I get the same answer. Okay, so this function is just another way of writing the given function. All right, so now let's think about our end behavior. We already know that it's not going to have a horizontal asymptote. So let me then ask you to do some quick thinking and some exploration. What happens to this function, f of x, as x gets increasingly large, other than the fact that it goes to infinity? What do you notice about any part of it as x gets very large? And what I hope you come to realize is that as x gets very large, what happens to this part right here? So as x goes to infinity, 7 over infinity minus 2, that just goes to 0. And so what that tells us is that as x goes to infinity, our function is going to give basically the same results as 3x plus 1 does. So as x goes to infinity, and I plug in like a million, I could go ahead and plug it in to this function right here. But what I could realize is that this chunk of it is just going to give me a result of 0. So the real power is just happening at 3x plus 1. What does that mean? That means this is what's known as our slant asymptote. It's the non-remainder portion. So our slant asymptote is the equation y equals 3x plus 1. Again, why? For the exact same reason we have a horizontal asymptote. As x gets increasingly large, if your horizontal asymptote is 0, then your function's behaving just like the equation y equals 0. In this case, as x gets increasingly large, our function behaves just like the equation 3x plus 1. So if I graph 3x plus 1, so it's y-intercept of 1, slope of 3, 1, 2, 3 over 1, 1, 2, 3 over 1, 1, 2, 3, 1, 1, 2, 3, 1. This is an asymptote. This is an asymptote. Label it, y equals 3x plus 1. Our vertical asymptote is at 2. X equals 2. We have no other vertical. We obviously have no horizontal. What else do I know? I have a y-intercept at 0, negative 5 halves. So that would be 2.5. I might have some zeros. I have not figured that out yet. So I need to figure out when 3x squared minus 5x plus 5 equals 0. I'm just going to use the quadratic formula. So I'm going to get 5 plus or minus b squared, so 25 minus 4 times 3 times 5. And I'm going to stop right there because I can tell already that I'm going to only have imaginary zeros because that's going to be a negative under the radical. So zeros, there are some imaginary ones, but basically what that means is there's no x-intercepts. All right, so once again, I would say the lack of data is data itself. So, keeping in mind the behavior at a vertical asymptote. So, stay with me. At a vertical asymptote, I either have to be coming up the vertical asymptote or I have to be coming, essentially down the vertical asymptote. So, we've got one of those two scenarios. The other issue is I have my slant asymptote. So just like a horizontal asymptote, what that's saying is eventually this graph that I'm drawing is going to have to come up and approximate that line. So it's going to approach that line. So it would have to look like this, or it'd have to come down, and then at some point it's going to have to curve back up and follow that line. So based upon our understanding of what happens at asymptotes and our lack of x-intercepts, we know that this option is not possible. So it has to be there. And then we look on the other side, and I know that I either have to be coming down my asymptote and then end up following My slant asymptote really should be closer than that, but that would be impossible. So that's not going to be the answer. Or it's going to have to come up the asymptote, not cross the intercepts, right? And there's no x-intercepts, and eventually curve down and hit that point and then follow the asymptote. And so our function is going to have to look something like that. In class, when we do this, we will probably look at it on a calculator. I don't have my calculator loaded up to show on this video, so we're just going to have to assume that we checked on the calculator and it looks right, because guess what? It does. So this would be our graph. All right, let's move on. Let's try another one. All right, we have the similar situation. Our degree on the top is bigger than the degree on the bottom. So this is not going to have a horizontal asymptote. We better factor this before we make any more decisions, or attempt to at least. 8 times 2 is 16. 8 minus 2 is 6. So yeah, that's going to work. X and 8 and 2, and it looks like a negative 8 and a positive 2, because I need a negative 6x. And this is going to be x minus 2. So don't get sucked into thinking they're going to factor and have that cloud your judgment on your factoring, because it almost did for me. When I saw that we're going to have an x and a 2, I figured they were going to cancel, but that would have been incorrect. So that means we do have a vertical asymptote. That's the main reason I now have done that. And that's going to be at x equals 2. I have zeros this time, and that's going to be at 8, 0, and negative 2, 0. I have a y-intercept, I assume, and I can find that back to the original. Plug in 0, negative 16 over negative 2. So I have 0, 8. All right, what have I forgotten? Horizontal, vertical, zeros. Now we need the slant asymptote. So once again, we're going to just do division. And we can go ahead and do it with synthetic this time. 1, negative 6, negative 16, and 2. So that's going to be negative 4. That's going to be negative 8, which is going to give us negative 24. So that means I can rewrite the function as x minus 4 minus 24 over x minus 2. So once again, this is sort of like the original. I can't use my clicker. It's very annoying. The original is like an improper fraction. And so this is just us simplifying the improper fraction and making it more or less a mixed number. And now, as we analyze our function as x goes to infinity, once again, we see that this term right here is going to head to 0 as x gets very large, which means we can just ignore it, and our function behaves just like the line y equals x minus 4. So we have a slant asymptote at y equals x minus 4. All right, let's put it on a graph. Vertical at 2. Slant. Slope of 1. All right, what do we got? Zeros at 8. 1, 2, 3, 4, 6, 7, 8. Negative 2. 0, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, I think we have everything we need to graph this. Once again, if we get lost in here, we just go to your vertical asymptotes and check the behavior. I either have to be coming up or I have to be coming down. So the logical situation here is I'm coming up because, and it's probably curving out long before, and I'm approaching my slant asymptote as I go on. So I've made it look a little bit too linear. Um, Probably it's more, let's see if I can clean this up a little bit. It's probably coming in more like this. It's probably just a very much more gentle curve. It could not be this guy, right? Because then I would never get that zero, or I'd have additional zeros or something. On the other side, I could either be coming up, but I don't understand how I'd be coming up, hit this zero over here, and then come back down. And what about the zero? What about the y-intercept, right? So all the information on this end is pointing to the fact that we're coming down and then looking like that. All right, let's see what else we've got. I've got one more for us here. Okay, we are in a slant asymptote situation, not horizontal. But before I make any other thoughts on this, I'm going to factor, or try to. I can factor out a 3x on top, leaving me with x squared minus 6. Is that right? Okay, interesting. And on the bottom, I don't know if it factors. I'm going to try. Let's see what we can come up with here. It'll have to be a 3x and an x. 6 makes 18. 1, that's not going to work. 3 and 2. 3 and 2 is the answer. Put a 3 here, that makes a 9. Put a 2 here, that makes a 2. 9 minus 2 is 7. I need a negative, so that's going to be negative 9 and positive 2. So there we are. All right. So let's check out our vertical asymptote. Looks like we're going to have vertical asymptote at x equals negative 2/3. If you can't do that in your head, go ahead and show the math. And x equals 3. No horizontal, no holes, zeros. X squared minus 6 is going to have some zeros, and as will 3x. So I'm going to get a 0 at x equals 0. In other words, 0, 0. And I'm also going to get some zeros at x squared equals 6, or x equals positive negative the square root of 6. So that means I've got one at root 6, 0, and one at negative root 6, 0, along with 0, 0. I don't need to find the y-intercept because it has already been found. It is 0, 0. So last thing we need is our slant. Have to do long division on this one. 3x cubed minus 18x squared. I'm going to throw on a 0x and a 0 on the end in case I need them. 3x squared minus 7x minus 6. That's going to be an x. X times 3x squared is 3x cubed minus 7x squared and minus 6x. I'm going to subtract, which gives me, let's see, negative 11x squared plus 6x. Ooh, ugly. How do I turn a 3 into a negative 11? I would have to multiply it by negative 11 thirds. Or, said another way, just divide 11x squared by 3x squared. Either way, you get negative 11 thirds. Multiply, and I get the 3's cancel, negative 11x squared, as designed. I get a bit of a train wreck after this, but let's see if we can figure it out. Negative 11, a negative 77, positive 77 thirds, and then minus, plus, let's see, 3 goes into 6 two times, plus 22. All right. Now I'm going to subtract, and I'm going to be left with some number x minus 22. But this would be my what? Remainder. And if you remember, or if you've noticed, we don't actually care about what the remainder is. We just know it has a remainder. So this we could say is plus something over 3x squared minus 7x minus 6. And once again, what happens to this as x gets very large? This whole piece right here, because the power on the bottom is bigger than the power on top, right? We're actually the first power on our remainder. Then this whole thing goes to 0. And so we are left with a slant asymptote of simply y equals x minus 11 thirds. All right, let's see what we know. Vertical asymptote, negative 2 thirds. I'm going to estimate that's that location. Very close to there. X equals 3. Make sure you label. I have a 0 at 0. I have a 0 at positive root 6. Square root of 4 is 2. So this is something 2 point something. So I'm going to say I have a 0 right in here. And then I have one at negative square root of 6, which is negative 2 point something. So I'm going to say we have a 0 right there. And I should label those. Negative root 6, 0, root 6, 0, and of course, 0, 0. And then I need to get my slant asymptote in there. Negative 11 thirds is going to be what? Just shy of negative 4. So here we go. 1, 2, 3, and 2 thirds. So right in here, we'll say. And then I have a slope of 1. So I'm going to go up 1 over 1, up 1 over 1, up 1 over 1. Still hanging on in that little 2 thirds area there. Okay. This is what we know. And I think we have almost everything we need. And the absence of zeros on the far right side, right? There's no zeros here. So that tells me I can't be coming up. I'm going to have to be coming down and then curve to my slant asymptote before we reach 0. On the far left, I can't be coming up and follow because I've got my 0 up here. So that means I'm going to have to probably be coming down and then curve to my asymptote like that. And then I've got to figure out the middle. The middle could be coming up or down. We don't know. So I need to explore. So I'm going to do a little exploration. I'm going to say as x approaches 3 from the negative side, so 2.9999999, what is y doing? So I'm going to come over to my factored problem, and I'm going to plug in 2.99999 and look at each factor. So 3 times 2.99, that's a positive. Anything squared is positive, but now it's minus 6. So what am I plugging in? Almost 3. 3 squared is 9. 9 minus 6 is positive. I'm not doing quite 3, but I'm doing very close to 3. So it's close enough. We know that that's positive. The bottom, we've got 3 times my almost positive 3 plus 2. That's obviously positive. And then I've got my number slightly less than 3 minus 3. That's a negative. So that means the whole thing is going to be negative because we have a positive divided by negative. So with that, I feel pretty darn good that my graph is coming up this asymptote, hitting that 0, hitting that 0 on its way back down, and then not actually crossing it like mine did, but close enough. Okay. I think that about does it for this unit. We will practice, 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 and hopefully get all of your questions answered. Thanks for hanging with me on this super long video.